Alrighty, in this video here, we're going to be talking about 4.3, the multiplication rules and conditional probabilities. Our third objective is to find the probability of a compound event using the multiplication rules. All right, so multiplication rules can be used to find the probability of two or more events that occur in sequence. The events are independent if the probability of the second is not changed by the occurrence of the first. Meaning, if I was to randomly select a card, put the card back, it is independent events. One does not affect the other. So again, independent events are when two events, A and B, are independent if the fact that event A occurs does not affect the probability of B occurring. So, for instance, rolling a die and getting a 5, and then rolling the die and getting a 3. Every time you roll a die, you have the same opportunity to get all 6 numbers. The fact that I got a 5 the first time will not affect me getting a 3 the second time. Or drawing a card and getting a queen, replacing the card and drawing a second card and getting a queen. By replacing the card, the second selection is from the entire deck, so it did not affect the probability of the second card. So the first multiplication rule is when two events are independent, the probability of both occurring. So that means now the word and. So meaning I want this to happen and this to happen, you multiply. So the big things here is the word and. So again, or we add, but now and we multiply. So you'll see I'll multiply the two independent probabilities. So again, the rule can be extended to 3 or more independent events. What that means is maybe I had 3 or 4 or 5 events I wanted to judge. As long as they're all independent, I can keep multiplying their probabilities as much as I want, as long as they don't affect each other. All right, so if a small sample is selected from a large population and the subjects are not replaced, the probability of the event occurring changes so slightly that for the most part, is considered to remain the same, even though the events are independent. So, for example, if 24% of Americans, consumers, prefer a particular brand, then if two Americans are selected, even without replacement, the probability that both prefer the stated brand would be independent. Meaning all I would have to do is multiply the two. So I would go 0.24 times 0.24, and we'll just come over here. So 0.24 times 0.24 gives me 0.0576. So meaning if I wanted to randomly select two Americans that like this brand, and it doesn't matter if I don't replace them, I have a 5.76% chance that I would select two of the same people that like that brand. The reason that we don't have to worry about replacement here is because out of America, there's millions of people here. So therefore, if we just remove one person, it's not going to affect the percentage of the people that are still left. It'd be different if I was selecting people out of a classroom and not replacing that student. That has a bigger impact. So let's look at example 13. Probability with replacement. So a jar holds 5 red marbles, 3 green marbles, 7 blue marbles. One marble is selected and its color noted. Then it's replaced. A second marble is selected and color is noted. Find the probability of each of the following. So for part A, it says selecting two green marbles. So I have three out of, what's that, 8, 15. So I have 3 out of 15 um, that would be green. But the fact that I'm taking this green marble and I'm putting it back in the bag, I would still have 15 marbles to choose from, and I would still have 3 marbles to choose from. When you multiply that, you get 1 out of 25 in the calculator, which comes out to 0.04 or a 4% chance of selecting two green marbles with replacement. Part B, first selecting a blue marble, so that's 7 out of 15, then a green one. So again, I'm putting that blue marble back in the bag, so I still have 15 marbles, and I would have 3 green ones. Multiply that out. In the calculator, you get 7 out of 75. Type in the calculator, you get about 0.0933. All right. Let's look at C. Selecting a red marble. So this is now 5 out of 15. Then a blue one. So that would be 7 out of 15. And then a green one. So that would be 3 out of 15. Notice the denominator never changed because every marble I'm taking out, I'm putting it right back in for the next selection. So the total marbles that there are never changes. When you type that into the calculator, you do get 7 out of 225, which is about 0.0311. So meaning you have a 3.11% chance of selecting a red, then a blue, then a green with replacement. All right, so now let's look at dependent events. So dependent events are when the outcomes or occurrences of the first event does affect the outcome or occurrence of the second event in such a way that the probability is changed. In this case, the events are called dependent events. So this time, if I don't replace the marbles, now it affects the next selection. So therefore, in that situation, it would be a dependent situation. So in example 14, we're going to classify each event as either independent or dependent, meaning does the first one event happening affect the second one? So here we go. So part A, having a large shoe size, that's the first event. Does it affect having a high IQ? Well, after the last studies I've seen, I see no correlations of shoe size to IQ. So this right here would be independent of each other. Having a large shoe size does not mean that you'll have high IQ, and vice versa. Having a small shoe size doesn't mean you'll have a high IQ. So they're independent of each other. Part B, a parent being left-handed and having a child who is left-handed. Well, believe it or not, that can be hereditary. So if a parent is left-handed, their child could also be left-handed. Doesn't mean they will, but they could, and a left-handed person has a higher probability of having a left-handed child than a right-handed. So in this situation, this would be dependent. Part C, getting a raise in salary and purchasing a new car. Well, if I'm getting a raise in salary, I get more money. If I get more money, I can buy new things. You specifically put it to a new car. That could be dependent of each other. Because if I don't get a new raise, perhaps I'm not buying a new car. So getting a raise in my money, I can put more money down on purchasing that new vehicle. Here's this fourth one, rolling a die and then tossing a coin. So if I roll a die on one, it has no effect if I toss a coin and get heads. So these two will be independent of each other. So again, if the first event influences the second event at all, for instance, more money, more purchases, or certain hereditary gene that you have will move down into your child. If one event influences the second, then it's dependent. It doesn't, independent. All right. So with that, let's get into conditional probability. Conditional probability of an event B in relationship to event A is the probability that event B after event A has already occurred. So conditional probabilities is basically stating if I want to know what the probability that event B happens, knowing that event A did happen. So for instance, let's see, what's one on the top of my mind? I don't know. Let's say I wanted to get a green marble on the second event, but I know they got a red marble on the first event. All right. So that's a conditional probability. So knowing what the probability of one event is, knowing that the first event did occur. So the conditional probability of event B, given that event A has occurred, is denoted by this. So what's the probability of this guy given this guy? So this is the probability you're looking for, but the fact that the first event did occur. So for instance, if an ace has already been drawn and not replaced, then the probability that a king will be drawn, given that the first card is an ace, will be 4 out of 51. And basically what they did. So knowing that the ace was already drawn, that means I now only have 51 cards to choose from. And then I have 4 kings. So again, the fact that the first event happened affects the second event, but knowing that the first event did happen, I now can say, all right, this is my new one. However, the probability of drawing an ace the second draw, given that the first card is an ace, is well, there's 4 aces, right? So if I know the first card is an ace, I know there's now 51 cards. But if the first card was an ace, and I want to know what the probability that the second card is an ace, I now only have 3 aces to choose from, right? Which actually comes out to 1 over 17. So again, probability that event B given event A has happened. All right, so let's look at the multiplication rule. So in the multiplication rule number 2, we're going to look at when 2 events are dependent, the probability of both occurring is the product of the probability of the first event and the conditional probability of the second event. So when I'm looking for the probability that A happens and B happens, really what I'm doing is find the probability that P happened, or sorry, A happened, and then I'm going to find the probability of B given A already happened. Right? It should be noted, though, that if 2 events A and B are independent, the event of B happening given A will actually be the same thing as what's the probability of B happening, since there is no change to the probability of event B when event A has occurred. So let's look at an example. Probability without replacement. So we're going to consider, again, a deck of playing cards. It has 52 cards in it. If you're not familiar with the deck of cards, do play a game with your friends so that you can get familiarized with the deck of cards. There's a lot of those examples in this chapter and on the homework. 3 cards are drawn and not replaced, right? So that means that the second and third card are affected by their previous cards. We're going to find the probability of the following events. So probability of A happening. So probability of drawing 3 10s. All right, so each suit has a 10 in it, and there's 4 suits. So I have 4 out of 52. All right, that's the first option. Times, knowing I drew a 10 the first time, I now only have 3 10s to choose from and 51 total cards. For the third one, knowing that the first and second both were 10s, then this third option would now only have 2 10s to choose from out of 50. So therefore, this would be my outcome. which comes out to be about 1 over 5,525, which is about 0.0001809. All right, there we go. Oh, nine actually. All right, so then the next one. Drawing a jack. So there's four jacks, one jack in each suit. So that's 4 out of 52. Then a queen. All right, so now there's only 51 cards. If the first one was a jack, I will still have four queens to choose from. And then the third one is a king. All right, so knowing that the first one was a jack, the second was a queen, I now only have 50 cards to choose from, but I still have four kings. So this would be a jack, a queen, and a king. And then I would just multiply this out. It actually comes out to about 8 over 16,575, which is about 0.0005. All right, part C. Trying to do this all the same. Drawing three hearts. So there are 13 cards in each suit. So that means there are 13 out of 52 cards. If I want the second one to be a heart, now there's 12 out of 51 hearts. If I know that the first one's a heart and the second one's a heart, the third one now only has 11 hearts to choose from out of a total of 50. So therefore, when I multiply this out, I actually get 11 over 850, which is about 0.0129. So you basically have a 1.29% that you're going to be drawing three different hearts. All right, part D. Drawing a heart first. So that would mean that there's 13 out of 52 options. Getting a club second. So that would be 13 out of 51. So again, if the first one was a heart, I now have only 51 cards, but does not affect the clubs itself. And the spade third. So that'd be 13 out of 50. So again, knowing that this one was a heart, this one was a club, this would be a spade. So in this case, that would be 169 over 10,200, which is round about 0.0166. So you have about a 1.66% chance of getting one card of each heart, a club, and a spade. All right, so let's move now to objective 4, which is finding the conditional probability of an event. So let's first talk about conditional probability formulas. So the conditional probability of an event B in relationship to an event A is the probability that the event B occurs after event A has already occurred. So the formula for conditional probability is this right here. So if I want to know what the probability of event B happening given the event A happened, you would take the probability of A happening and B happening divided by the event A happening. So for instance, if I know the probability of getting a heart is 13 out of 52, and now I want to know what the probability of getting a heart and um, I don't know, get a diamond or something like that. That will now be, so I got 13 out of 50. That's the total. That's our hearts. Now this one's a heart and a diamond. So let's do a heart and a two. That would be 1 out of 52. So in this case, that would basically be a 1 out of 13 chance of getting a 2 out of hearts, given that I got hearts the first time. All right, so let's see if we can get a better example of that. Let's look at example 16. So if we look at incarcerated population, So in a recent year, 0.99 of the incarcerated population is adults, and 0.07 of the incarcerated are female. If an incarcerated person is selected at random, find the probability that the person is a female given that the person is an adult. So here we go. So when we're given the event A being an incarcerated adult and event B being female, we're looking for this probability. So event A and event B we know is 0.007 and the event A is 0.99. Okay, so um, again, when you find the probability that the person is a female, given that they're adult. So instead of looking at the entire population, we're only going to look at the entire population that they are adults. So 0.99 would actually go on the bottom. So that's the event A happening. They are an adult. Now the probability that they're an adult and they are female. So if they're both an adult and a female, that would be what goes on top, which is 0.07. So if I want to know the probability of selecting a female that happens to be an adult, would be 0.07 divided by 0.99, which comes out to 0.707. So you're looking for the probability of event B happening given A, whatever the event A is becomes the new total on the bottom. And then you just find the probability of both B and A happening, and that will go on top. Let's look at another example. Look at example 17. So in example 17, we're talking about a country club. So at a local country club, 73% of the members play bridge and swim. 82% of the members play bridge. If a member is selected at random, find the probability that the member swims. All right, so this is the number that goes on the bottom. So start there, given that the member plays, no, sorry. So find the probability that the member swims, given the member plays bridge. So this right here will be the number that goes on the bottom. So we have players that play bridge and swim. So members play bridge and swim is 0.73. People that play just bridge, or sorry, it doesn't say just bridge, but plays bridge is 82. So now I want the probability of this. So people that play bridge, that's going to be 0.82 on the bottom. That's my new total. Now, how many of them swim? So that means how many of them swim and play bridge? That's now 0.73. So when we divide these two up, we actually get about 0.8902. So you have an 89% chance of selecting someone that swims given that they played bridge. All right. So probabilities for at least. So if you want to find the probability of at least getting a 4 or greater, right, on a die or some concept like that. So the multiplication rules can be used when the with the complementary events rule to simplify solving probability problems involving the word at least. So if I want a probability of at least one happening, I can do 1 minus the probability of none of them happening. All right, that's just one of the type of example that we can use to help simplify some of our math. So let's look at example 18. It says at least one paid assistantship. So of PhD students, 60% have paid assistantships. If 3 students are selected at random, find the probability that at least one has a paid assistantship. So to do that, so probability of at least one of 3 PhD students had a paid assistantship. What we can do is we can say 1 minus none of them being an assistantship, and then we would have our total versus having to figure out 1, then 2, then 3. So that's the issue with at least. If I want at least 1, then that means I have to find the probability of 1, probability of 2, and the probability of all 3 of them. But this is the same thing as saying All right, let's take this away. What's the probability that none are it? If I can take that part out, then I'll get at least one or greater. Because technically, to find the total, you would have probability of none, probability of one, probability of two, and the probability of three. So by taking out the none, I'll be left with the other three options. So this is my what you would call the sample outcomes. I can either have no paid assistantships, one, two, or three paid assistantships. If I take this total to add these up, I could be here for a while. Instead, I could just find the probability of none, take away from one, and I'll be left with the probability of all three of those in just one step. So here we go. So a probability of a PhD student having an assistantship. So a PhD assistant student that has an assistantship. So that would be 60%. So that'd be 0.60. So a PhD student that does not have an assistantship would be 1 minus 0.60, which is 0.40. So none of the three PhD students has an assistantship would be basically 0.40 times 0.40 times 0.40. It's not going to be adjusted because we're assuming there's a large population here. So when we multiply these all out, this is a multiplication, we get 0.064. So to have at least one, we can do one minus none of them being paid, which then comes out to about 0.936. So we have a 93.6% chance that at least one of the three students we select will have a paid assistantship. All right, let's look at one more. So in example 19, it says at least one rose. So in a bouquet, there are six roses, nine lilies, seven daisies, and six orchids. If four flowers are selected at random and not replaced, we want to find the probability that at least one of the flowers, so find the probability of at least one of the flowers is a rose. So it'd be better to find the probability of at least one rose would be the same answer as one minus no roses. So in this case, I could go and how many? So if four flowers are selected. So I can go one minus, so none of them are roses. So that would mean there's 9, 16, 22 out of 28 flowers. The second one, there would be now 21 out of 27. The third one would be 20 out of 26. And then the fourth one would be 19 out of 25. So we find this, we now have our total. So we multiply that out, turn it into a decimal, we get 1 minus 0.3573, which comes out to 0.6427. So you have a 64% chance of selecting four flowers and none of them, or at least one of them, sorry, at least one of them being a rose. Part B says the probability that all four are roses. So this would be easy just to do all four. So first one being a rose is 6 out of 28. Second one being a rose would now be 5 out of 27. Third one being a rose would be 4 out of 26. Last one being a rose would be 3 out of 25. When you multiply this out, turn it into a decimal, you get 0.0007. Part C is either event likely to occur. Really and truly, I would say event A has a likelihood of occurring. Event A is more likely to occur, meaning out of four flowers, at least one will be a rose with a 64.27% chance. Versus all four of them being a rose, you have less than 1%. Right? So just kind of looking at the evidence there. That was pretty much it on that question. All right. Those are a lot better examples. So if you have any more questions or need more examples, please reach out and let me know. I'll see you in the next video.